We've gone for main engine start. We have
In 1981, Space Shuttle Columbia lifted off into the Florida skies, ushering in not only a new era of spaceflight, but also introducing a new concept to those outside the space industry, that being the concept of reuse. Now in 2026, reuse is not only commonplace, but expected, with many examples from the last 2 decades being New Shepard, Falcon 9, New Glenn, Crew Dragon, Starliner, Orion, Starship. Indeed, Starship is to some the holy grail of reuse, with plans to reuse every part of the vehicle, something not presently achieved by any other vehicle in spaceflight. But before reuse became what it is today, it largely started with the Space Shuttle.
It's called the Reusable Space Shuttle. Taking off like a rocket and landing like an airplane, it will virtually replace the way we transport manned and unmanned spacecraft into orbit by the early 1980s. To prepare for the shuttle, research and development programs continued to move ahead as high-speed wind tunnels were used to help solve the problems of re-entry. Here, undergoing tests, are special recoverable booster rockets that will be retrieved after launch. Other engineers prepare to make shuttle vibration studies, finding out where the stress areas are.
But many people argue that it was only refurbished, not reused, or that it had to be disassembled after every flight. But was it so far from reuse as so many make it out to be? Well, let's start looking through each major part and talk about how they were reused. Also, for this video, I won't be deep diving into what each part of the vehicle is or its role in the system, given the Space Shuttle is one of the most iconic and well understood launch systems in history, given its 30-year operating life. Without exaggeration, the shuttle is so well known and so iconic that I meet people today in 2026 who see my photo in front of SLS and call it a shuttle. True story. So without further ado, let's focus on the twin solid rocket motors that boosted the vehicle into the upper atmosphere before being jettisoned. After each use, the boosters fell back to Earth, splashing down under the aid of parachutes, except for STS-4, where the main parachutes failed to deploy. This was caused by a timing mechanism in both of the boosters, which caused the main parachutes to deploy too early. Being fired that early, they were still under high dynamic pressure, which resulted in 2 of the 3 parachutes being torn off. As a result, the boosters impacted the Atlantic at excessive speeds and resulting in their destruction. After a nominal splashdown, each of the boosters was tugged by boat back to port. Then they are transported by train to Utah to be inspected and have their solid rocket repellent refilled, as well as having their seals reinstalled before finally being shipped back to Florida for reflight. What's reused on the boosters are the white steel casings that make up the booster segments. The seals, insulation, and other gaskets, like O-rings, are disposed of and replaced for every flight. Another component that is reused is the hydraulic power unit, or HPU, and the auxiliary power unit, or APU. The HPU and APU are located inside of each booster's aft skirt, and they provide power to the thrust vector control system that allows the booster's nozzle to move in flight. Each of these components is designed to be reused and reflown up to 20 flights before replacement. Atop of each booster inside the forward skirt is the Rate Gyro Assembly, or RGA. These gyros provided the orbiter with pitch and yaw data during launch. Once the boosters were jettisoned, the orbiter would switch to its own onboard set of gyros to continue to manage its orientation. These sets of gyros could fly up to 20 missions before being replaced. After reviewing a ledger that recorded each segment's flight history, the record holder for the most reflights is an external tank attachment ring with 14 flights, with a frustrum having 12 flights and several case segments having up to 10 reflights, noting that segments and components could be swapped, not necessarily flying with the same booster casings as previous flights. Now in 2026, the Space Shuttle SRBs continue to live on, albeit very briefly, as they help to propel the SLS core stage into orbit on every flight. However, unlike with the Space Shuttle, these boosters are not recovered.
But why?
There are multiple reasons why these boosters are no longer recovered. Firstly, the reuse of the booster segments has cost NASA more to manage compared to just making new expendable boosters on every flight, which NASA ultimately plans to do when they run out of Space Shuttle SRB components. These plans to replace them with cheaper, more powerful composite designs are known as BOL, or the awkwardly named Booster Obsolescence Life Extension, beginning operation on Artemis 9 as part of SLS Block 2. And in a future video, I'll go over just how much of the SRBs powering SLS is truly shuttle stock versus new hardware. Another reason why they aren't reused is because of the increased skill and equipment needed that goes beyond what was done with the Space Shuttle boosters. After splashdown, each of the boosters needed their nozzles plugged to maintain their buoyancy for transport and recovery. This was achieved using typical scuba divers. However, with the new 5-segment boosters, standing 28 feet or 8.5 meters taller than the Space Shuttle boosters, the new depth the booster nozzles would descend to under the water would require deep sea diving gear due to the pressures involved. That's more expensive gear, along with the more expensive training to prepare and get the recovery crews ready to plug the nozzles, making the already costly prospect of the boosters' reuse even more expensive and even less practical. And it's important to note regarding the boosters that the initial prospect of their reuse was to achieve the goal of a mostly reusable launch system, which in the early 70s was seen as a radical idea.
This animation shows how they work during launch. The two solid rocket boosters strapped to each side carry their own propellants and burn for about 2 minutes before separating. Their onboard parachutes will then bring them back to Earth for recovery and reuse.
NASA never intended the boosters to stagnate as they did, as NASA had plans for a 5-segment design, which would be evolved to power SLS, along with a carbon fiber design, which would also be evolved into the SLS Block 2 design of BOL. However, after the tragedy of Challenger in 1986, much of the development work on these boosters were frozen, slowly picking up speed through the 90s, only for these upgrades to be cancelled after the Columbia disaster in 2003. Moving on from the boosters, the main part of the shuttle launch system was the orbiter itself, with the Space Shuttle Discovery setting the record as the most reflown spacecraft in history at 39 flights. But what on the orbiters is still on it from when they left the factory in Palmdale, California? Starting from the center, the airframe is the core structure that makes up an aircraft, or in this case, spacecraft. Needless to say, the airframe of every orbiter remains largely the same, though occasional repairs and reinforcements were added as mission needs required. One of the most often criticized and slandered parts of the orbiter for its extensive downtime and making it only refurbishable rather than reusable is the approximately 24,000 black and white thermal tiles that cover the orbiter and protect it from the heat of re-entry. The vast majority are black silica tiles, making up approximately 62.5% of all orbiter tiles. These tiles were extremely light, at an average weight of 5 to 6 ounces each, and are filled with silica foam. This is an example of a thermal tile I personally own. Though not from the Space Shuttle program, this is surplus stock from the Soviet Buran program, but its design is largely the same. But how many of these black thermal tiles are still on the orbiter from its original rollout from Palmdale? Well, engineers from the United Space Alliance, a joint venture formed to manage the orbiters, estimated that 18,000 of the original thermal tiles are still in place on Discovery. This is even visible as a result of Discovery's unique teardrop tile arrangement around its cockpit, something it rolled out with in 1983 and still has to this day. One NASA document cited that approximately 50 tiles had to be replaced after each mission, meaning that after Discovery's long operational life of 39 missions, an approximate 1,950 tiles had to be replaced. Much of the orbiter's thermal protection system was designed to last up to 100 missions if they passed inspection. meaning that the original tiles remaining on Discovery are only through 39% of their certified operational lifespan. Moving inwards inside the orbiter is the cockpit and avionics, of which most remained in place or were upgraded by newer systems. The orbiters underwent a glass cockpit upgrade starting in 1999, replacing the older cathode ray tube displays with newer electronic displays.
Significant updates for NASA's fleet of space shuttles was the installation of the Multifunction Electronic Display System, or MEDS, in the shuttle's cockpits, making the orbiter safer and easier to fly. The glass instruments gave the cockpit a unique appearance which suggested its well-known name, the glass cockpit. The new display system improved the handling of the vehicle using easy-to-see flight information, such as the attitude, altitude, speed, and many indicators the astronauts need to know during liftoff, landing, and for navigation. The electronic system included 11 full-color flat-panel display screens in the shuttle's cockpit. The screens replaced 32 gauges and electromechanical displays and 4 cathode ray tube, or CRT displays. It's 75 pounds lighter and used less power than the older system. NASA research eventually led to the Federal Aviation Administration's certification of electronic flight displays, and MEDS became mainstream equipment on all commercial aircraft. What's important on a commercial airliner also is beneficial to the astronauts flying the shuttle. Space Shuttle Atlantis was chosen as the first orbiter to receive the glass cockpit during its 1998 modification period, and lifted off with its new cockpit display on the STS-101 mission in May of 2000. Shuttle Endeavour was the last spacecraft in the fleet to be outfitted with the electronic display and made its first flight with the improved system in August 2007 on the STS-118 mission. The glass cockpit still remains one of the most important modifications in the orbiter fleet to safely fly out the final missions of the program.
However, not every part was upgraded or replaced. Many remained in use on the orbiter until a discrepancy was found and was replaced, leaving much of the original orbiter's internals still in place. This is clear when Space Shuttle Columbia landed at the White Sands Missile Range in 1982 at the end of STS-3. However, when Charlie Bolden flew on Columbia on STS-61C in 1986, 4 years and 21 flights later, he reported that gypsum dust from STS-3's lakebed landing was still coming out of Columbia's crew compartment. At the rear of the orbiter is the Space Shuttle's engines. A pair of AJ-10s form the Orbital Maneuvering System, or OMS. Below them are 3 RS-25 Space Shuttle main engines. All of these engines are designed to be removed, inspected, and have any parts replaced before reinstallation for reflight. This process, though lengthy, is where much of the complaints about reuse or refurbishment begins to stem from. While most of these engines are reused, internal parts are replaced rather than the whole assembly inspected in place like we see on newer, modern spacecraft. The OMS operated under much less strenuous conditions and flight loads, meaning they could be reused with less maintenance compared to the RS-25 Space Shuttle main engines. With the OMS engines designed for up to 1,000 starts or 15 hours of cumulative firing time. To process each RS-25 after every flight, the orbiter is rolled to one of 3 orbiter processing facilities at the Kennedy Space Center, at which point each engine is removed from the back of the orbiter. Then these engines are shipped off to a Space Shuttle main engine processing facility to be inspected and have select components disassembled for future analysis, after which they are shipped off to the Stennis Space Center for acceptance testing. Once certified for flight, they are returned to the Cape to be reinstalled into an orbiter for a future launch.
T-minus 15 seconds. 12, 11, 10, 9, 8, 7. We have a go for main engine start. We have 3 main engines running. 3, 2, 1. And have main engine cut off. GLS safing is in progress.
That's assuming there's no other issues leading up to launch, as was occasionally the case. While some issues could be fixed at the pad, occasionally the orbiter had to roll back to the vehicle assembly building to have an engine replaced, such as the case of STS-41D, where a redundant set launch sequencer abort resulted in Space Shuttle Discovery being returned to the orbiter processing facility to have its engine swapped out, a process that took 63 days before they could make another launch attempt. This means that every launch did use a different set of RS-25 engines from the previous, though each engine often had its own extensive flight history, with engine 2019 accruing 19 flights between STS-9 in 1983 and STS-93 in 1999. Some engines did fly together repeatedly, such as engines 2005, 2006, and 2007. All three flew together across STS-1 through to STS-5, although that wasn't by choice. The engine pool to support this shuttle program was still small early on, so while new engines were being built and certified, these three continued to power Columbia into orbit for over 5 consecutive flights. There's other various parts of the Space Shuttle orbiter that hasn't been mentioned but all play a role, such as the tires on each orbiter, which were replaced after each landing due to the intense stresses put on them after each landing. Another example is the cockpit windows, which were inspected and only replaced if damage exceeded accepted limits, which often happened due to debris strikes while in orbit. Oh, and I didn't forget about the external tank. It just doesn't have much of a role in the discussion as it was the only part of the shuttle system designed explicitly to be disposed of after every flight.
After the solid rocket boosters separate, the orbiter and external tank, with engines still firing, continue to near orbital velocity at about 70 miles above Earth. The main engines will burn for 6 more minutes, then cut off. Almost 1.5 million pounds of liquid hydrogen and liquid oxygen have been consumed during the first 8 minutes of flight. Now the external tank will be jettisoned and fall into a predetermined ocean area, the only major component of the shuttle vehicle not recovered for reuse.
People sometimes ask why NASA didn't try to reuse that too, but the biggest issues were cost and engineering challenges. The external tank was designed to be made cheaply and in bulk. Making them reusable adds costs that might not be recuperated given the additional resources of recovering such a massive tank. Even if they decided to invest in recovering the tank, it would be quite difficult for a very small return, as the tank, unlike the boosters, would be traveling at just shy of orbital velocity, as each shuttle jettisoned the tank just shy of orbit for them to typically burn up near the Indian Ocean. All of these components and systems together made up the first reusable launch system and a reusable crewed spacecraft. While the shuttle is now antiquated against newer vehicles like the Falcon 9 or Starship, both were made possible thanks to much of NASA's work with the Space Shuttle, as SpaceX used NASA data on the thermal tiles to help design Starship's thermal tiles. The Space Shuttle also flew Dragon 1's docking LiDAR camera, known as Dragon Eye, which helped SpaceX to test and prepare for their eventual docking to the ISS in 2012, becoming the first private company to do so. Dragon Eye has even become the basis for Starship's docking system, bringing more Space Shuttle heritage to Starship's success. So, answering the question as to whether the Space Shuttle was a reusable launch system or merely refurbished, the answer is both. While some parts of the orbiter were reused and left in place for future flights, others, like the engines, would be removed and go through a lengthy refurbishment period before they could fly again. The Space Shuttle was NASA's first attempt at a reusable system that could launch itself into orbit and the same parts be used time and time again. In doing so, some compromises were made, not all of them good, be it for cost and time saving, and most certainly not for safety. But they were nevertheless an experimental leap forward that enables the massively reusable world we enjoy today.